Now we're going to start talking about what actually causes the motion. So that's the subject of dynamics. And we're going to start this discussion with the fundamental laws of motion, which are Newton's laws of motion. So basically we call the cause of the motion the external factor that affects the motion of an object, force. So force is defined as a vector quantity, so it has a magnitude and it has a direction. And we have two types of forces. We have contact forces. These are forces that appear when an object is in a physical contact with another object. For example, if you hit a ball, you have a physical contact with the ball. When you lean onto a wall, there is a physical contact between you and the wall. You exert a force on the wall exerts a force on you. These are contact forces. Field forces are forces that actually involve no physical contact. So these forces will appear even if there is no physical contact between the two objects. A good example is electrical forces. Another example is gravitational force. So these are forces that cause an action at a distance. Okay, so what are the fundamental forces in nature? We have four. First one is gravitational force between two objects. This appears between two objects whenever they have a mass. Electromagnetic force is between electric charges. There's the strong force that is in between subatomic particles, so that's in the nuclear scale. And there's the weak force in certain radioactive decay processes. So gravitational force, electromagnetic force, strong force, and weak force are four fundamental forces in nature. Now, let's start with Newton's laws of motion. Newton's first law is known as the law of inertia. So what does it say? If an object does not interact with other objects, so there is no external force, the object is free of any external factors that will change its motion, it is possible to identify a reference frame in which the object has zero acceleration. This is called an inertial reference frame. So if an object is subject to no forces, no external forces, or total zero external force, it's going to have zero acceleration as viewed from an inertial reference frame. And what is an inertial reference frame? The best approximation to an inertial reference frame is the one that moves with constant velocity relative to distant stars. So inertial reference frame is one that is basically not accelerating with respect to another inertial reference frame. So it's a non-accelerating frame, and it is defined with respect to distant stars. So if it has constant velocity with respect to distant stars, which are more or less at rest, so that's what we have in our approximation, then since it's moving with constant velocity with respect to distant stars, it's not accelerating, and that it is called an inertial reference frame. Any reference frame that moves with constant velocity relative to an inertial reference frame is itself an inertial reference frame, because using our Galilean transformation, if you remember, if we have a reference frame that moves with constant relative velocity with respect to another reference frame, then we're going to have this reference frame having a constant velocity with respect to distant stars as well, so it's going to be another inertial reference frame. Now, is Earth an inertial reference frame? Obviously, Earth is moving, it has an orbit, and it's actually spinning around its axis, so strictly speaking it is not, but it is an approximate inertial reference frame. Now, we can mathematically state first law by saying the total net force acting on an object is zero. Then we have the initial velocity of the object equal to the final velocity as viewed from an inertial reference frame. So maybe it's better to put a net force of 0 on the object, then we can say that the velocity of the object is not going to change as measured from an inertial reference frame. So what is a non-inertial reference frame? It's one that accelerates with respect to an inertial reference frame. Then this Newton's first law will not be satisfied when the motion is viewed from a non-inertial reference frame. One has to take into account the fact that it has an acceleration itself. So we're going to go back to this later on. And by the way, what is inertia? Inertia is the resistance to change in velocity. So that's basically a quantity that measures the resistance to change in velocity. So mass is an important property of an object that specifies how much resistance an object exhibits to change it in velocity. So mass is the measure of the inertia of the object. It is a scalar quantity, and so it has a magnitude and it has a unit. It doesn't have a direction. So the mass is defined by the effect of the force on the object, actually. So if you apply a force on mass 1, it produces an acceleration a1. If you apply the same force to mass 2, it produces an acceleration a2. Then we experimentally know that the ratio of these two masses, m1 over m2, is a2 over a1. So it is inversely proportional to acceleration under a constant force, and basically this is defining mass by looking at the response to this force. Now, what about weight? Well, the weight of an object is the magnitude of the gravitational force exerted on the object, and this varies with location because we have a change in gravitational acceleration in different locations on Earth, for example. So we can measure a different weight. Also, the measured weight on Moon will be different from the measured weight on Earth, obviously, because the gravitational acceleration will change. Okay, so that's Newton's first law. The net force acting on an object is 0. Its velocity is constant. It's not going to change when it is viewed from an inertial reference frame. If the object was at rest, it will remain at rest. If the object is moving with constant velocity, it will continue moving with constant velocity as measured by an inertial reference frame. And its response to the force is basically determined by its mass, which is the resistance to change in velocity, such that m2 over m1 is a2 over a1 under a constant force, and the weight of the object is on the other hand, the magnitude of the gravitational force that is exerted on the object. Now, Newton's second law. Now let's have a force, a net force acting on the object. So this states that the force is going to, acceleration that is caused by the force will increase as the force increases, and under a constant force, the magnitude of the acceleration is proportional to 1 over m. That's experimental fact. So using these experimental facts, Newton has formulated his second law. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So acceleration that is caused by the force is directly proportional to the force, inversely proportional to the mass. This is experimentally known, so this can be written as the net force acting on the object is equal to its mass, inertia, and acceleration a. So the force defined this way is measured in newtons in SI units. 1 newton is 1 kilogram meters per second square. Mass is measured in kilograms in SI units, and the net force is m times a. Now this is a vector equation, so that means the x component of the net force is m times x component of acceleration. Y component of the force is m times y component of acceleration. Z component of the net force is m times z component of the acceleration. So we use this summation to indicate that we are talking about the net force acting on the object as opposed to an individual force. Now, As I mentioned, the difference between mass and weight, we called the magnitude of the gravitational force on the object to be its weight. It's for an object on Earth, it's going to be due to the gravitational force on Earth, and gravitational acceleration on Earth is roughly 9.8 meters per second square on Earth. So we can use this quantity, and when we talk about the response of the object to the gravitational force, the mass that appears in this equation we can call gravitational or inertial mass. So basically this is one way to define mass here. Gravitational mass is the ratio of the gravitational force to the gravitational acceleration acting on this object. Okay, now let's come to Newton's third law. Now we have an interaction between two objects. One object is exerting a force on the other object. F12 is the force exerted by object 1 on object 2. This is equal in magnitude and opposite in direction to the force F21, force exerted by object 2 on object 1. So we can write this mathematically as F12 vector is minus F21 vector. So these are two objects, object 1 and object 2. So the force exerted by object 1 on object 2, this is going to appear on object 2. Force exerted by object 2 on object 1, this will appear on object 1. And these forces are equal in magnitude and opposite in direction. Now a good example, we put an object on a table. So the object is at rest on a table, and here is our coordinate system, x and y. So if I look at the forces acting on this object, obviously this object has mass m, and therefore it's under the influence of the gravitational force Fg, which is minus mg j hat. So j hat is the unit vector on the y-axis. And the net force acting on the object is 0 by Newton's second law. Why? Because the object is not moving, or we can say it's due to first law maybe, because the net force acting on the object is 0. So we should say probably first law here. And the net force acting on the object is the gravitational force plus a force that opposes the gravitational force, so that we will have 0 net force. That force that opposes the gravitational force is the normal force N, which is minus the gravitational force, which is in plus j hat direction and has magnitude mg. So this normal force exerted by the table on the object perpendicular to the table is basically in response to the force exerted by the object on the table, which was minus mg j hat. So the force, reaction force that is basically exerted by the table on the object is the normal force. So these two forces are equal in magnitude, opposite in direction. So Newton's third law is also known as action-reaction. Action-reaction law. So the action is the mass m exerting a gravitational force on the table. The table shows a reaction by exerting a normal force on the mass. So when we consider a mass to be concentrated to a particle, just to model the situation, we can plot all the force vectors acting on it. So we can model this m, the object with mass m, as a single particle. There is the gravitational force acting on it, and there is the normal force acting on it, force exerted by the table on the object, and those are the only two forces acting on this object. Then the diagram we will obtain by using this procedure is called a free body diagram. So a free body diagram is obtained by modeling the object as a concentrated mass to a certain point. So this has a mass m, and by plotting all the forces acting on the object, we obtain this diagram. Another good example for Newton's third law is when we have a block of mass m that is attached to the ceiling by using a rope. So a massless rope, so we're neglecting the mass of the rope, is attached to a mass m at rest. Now, as opposed to the object sitting on the table, now we have the string that will exert a force on this block in order to compensate for the gravitational force. So the total force acting on the object will be the force T exerted by the string plus the gravitational force. That is equal to 0. The object is not moving, so we can say, according to the first law, the object is not moving. Net force acting on it is 0. So the magnitude of the force the rope exerts on the object is how much? It's basically the magnitude of the gravitational force. And we have the net force acting on it is 0. The object doesn't move, but the fact that we have the force exerted by the object on the rope is opposed by a reaction force that is acting on this object in the opposite direction. So we could also say that the fact that we have a force couple here is T is equal to minus the gravitational force, because what is T? It's the force exerted by the rope on mass m is equal in magnitude and opposite in direction to the force exerted by mass m on the rope. That is third law. So this is basically saying that these two forces have the same magnitude, opposite in direction. Now, what is the magnitude of this force on the rope? It's called tension. So tension is a scalar quantity. It's not the force itself, it's the magnitude of the force appearing on the rope. Okay, so we have seen two examples of Newton's third law. If you have an object sitting on the table, the force exerted by m on the table is basically minus the force exerted by the table on object with mass m. That is third law. And in this case, it's the gravitational force that is being opposed by the normal force acting on the object. It's perpendicular to the object, so the normal force should be acting in this direction and making a 90-degree angle. On the other hand, if we have the object attached to a massless string, the reaction force to the gravitational force is the force appearing on the string, which has a magnitude we call tension. So the tension in the rope, the force that has the magnitude of tension is basically the tension force that is opposing the gravitational force that is exerted by the object m on this rope. So we can say that this FRM is minus FMR. So we can also say this is a force couple. It's a action-reaction case. Okay, so to summarize, we have talked about Newton's laws of motion. First law says, from an inertial reference frame point of view, that is a reference frame that is in constant velocity motion with respect to distant stars or with respect to another inertial reference frame, if the net force acting on the object is 0, its velocity doesn't change. It's a constant. If it's at rest, it will remain at rest. If it's moving with constant velocity, it will keep its motion with constant velocity. We have defined mass as the inertia or resistance to change in velocity, and the weight is the magnitude of it, the gravitational force acting on this object. Newton's second law says net force acting on the object is its mass times the acceleration, or the acceleration that is caused by the net force acting on it is F net divided by m. So that would be mathematically speaking, this is correct, but physically this makes more sense. A is due to the net force acting on the object, and it's inversely proportional to its mass. And this is a vector equation, and force has a unit of newtons. 1 newton is 1 kilogram meters per second square. So on the other hand, mass is measured in kilograms, as I mentioned here. Okay. So the magnitude of this gravitational force we called weight. We talked about this, and Newton's third law is about force couples. If you have two objects interacting, force exerted by object 1 on 2 is equal to minus the force exerted by 2 on 1. So we have a force couple. A good example is normal force on a table, and also another good example is the tension appearing on a massless rope when a block of mass m is attached to it. And by the way, we talked about the free body diagram, which is a very nice way to analyze the effects of the forces on the object. We model the object as a single particle with mass m concentrated to a point, and we plot all the forces acting on this particle to determine the net effect on the motion of the object. So in the next lecture, we will talk about different examples for Newton's laws of motion.